Welcome to the Deep Dive. Today we're all about energy and how it drives chemical change.
Yeah, going beyond just the basics.
Right. We're going deep. We've got this chapter from a chemistry textbook. And wow, it really dives into how energy makes these reactions happen.
Like the nuts and bolts.
Exactly. We'll unpack the whole potential versus kinetic energy thing.
Oh, yeah, that's a good one.
Like, imagine a roller coaster. All that energy as it goes up and down the track.
Perfect example.
And then get this. We'll even find out how scientists actually measure the heat released in a reaction.
Using a whatchamacallit, a calorimeter.
Right. And we'll tackle that big question, why are some reactions spontaneous, like, a bonfire?
Happens all on its own.
Right. While others need a push, like, when you're baking a cake.
You got to put in some effort there.
Totally.
Well, it all comes down to the fundamental principles of energy. How it interacts with matter.
Okay, so let's start with the basics. We're talking about the energy stored in the bonds of molecules, right?
Right. Exactly. That's where chemical potential energy comes in. It's all about how those atoms are arranged within a molecule. Think of it like a tightly wound spring.
Yep.
It's got all this store energy just ready to be released when you let go.
Ah, I get it.
And similarly, the way those atoms are bonded well, that determines how much energy is actually stored in those bonds.
So you break those bonds, rearrange the atoms, form new bonds.
Boom. A chemical reaction with an energy change.
So is that why some reactions release energy, like a bonfire giving off heat, while others need energy to get going, like baking that cake?
Precisely. Some reactions release heat into the surroundings.
Okay.
Those are called exothermic reactions.
Exothermic, okay.
And then you have reactions that absorb heat from the surroundings.
Gotcha.
Those are endothermic.
Okay, so that makes sense.
Like an instant cold pack. Think about that. It gets cold because the reaction inside is actually absorbing heat from your hand. Oh, that's a good way to remember it. So how do we actually measure all this energy being transferred around, especially when things are heating up or cooling down? Isn't there a difference between heat and temperature?
Yeah, you're right. A lot of people use those terms interchangeably, but they're actually two distinct concepts. Temperature measures the average kinetic energy of the particles in a substance.
Okay.
Imagine like a room full of people dancing. Temperature is like the average energy level of their moves.
Okay, fun analogy.
But heat, on the other hand, that's the actual transfer of thermal energy between objects at different temperatures.
So if someone with a high fever accidentally bumped into me, heat would flow from them to me because they have a higher temperature.
That's a great way to put it. And to measure this heat, we use units like calories and joules.
Okay.
A calorie is the amount of heat needed to raise the temperature of 1 gram of water by 1 degree Celsius.
Okay.
But don't confuse this with the calories you see on food labels.
Ah, yes, the dreaded food calories. Those are actually kilocalories.
Oh.
Or 1,000 calories.
Right. A bag of chips doesn't have the same energy as it takes to, heat a swimming pool.
Exactly. And then you've got joules.
Joules?
Joules are the SI unit of energy. 1 calorie is equal to 4.184 joules.
Okay.
Think of them as different currencies for energy. You can convert between them, just like you can convert, dollars and euros.
Speaking of water, I remember from the textbook that water has a surprisingly high specific heat.
Yes. Water has this remarkable ability to absorb a lot of heat without those crazy temperature changes.
Okay.
And this is crucial for life on Earth.
Oh, wow.
It helps regulate our planet's climate, and it protects organisms from these extreme temperature swings.
So is that why coastal areas tend to have more moderate temperatures than inland regions?
Exactly. The oceans act as these giant heat sinks, absorbing and releasing heat slowly. It keeps those coastal temperatures more stable.
That's incredible. It's amazing how this, seemingly obscure concept has such significant real-world implications.
Yeah, and it's this property of water that also makes calorimetry possible.
Calorimetry.
Yeah. A calorimeter measures the heat absorbed or released during a reaction.
Okay.
Essentially, it's a well-insulated container. It minimizes heat exchange with the surroundings.
So like a thermos.
Kind of. And I remember reading about different types of calorimeters.
Yeah.
There's the bomb calorimeter for combustion reactions, and then the simpler coffee cup calorimeter.
Right. For less extreme reactions.
Exactly. And the key assumption in calorimetry is that no heat is lost to the surroundings.
Okay.
Of course, in reality, there's always some heat loss. But scientists use all sorts of techniques to minimize it and make sure their measurements are accurate.
It's like trying to contain an explosion. You want to make sure all the energy stays within the calorimeter so you can measure it precisely.
Exactly. And by measuring that heat change, we can calculate the change in enthalpy. We denote that by a note.
Okay, hold on. Back up for a sec. What exactly is enthalpy?
Think of it as the total heat content of a system. We can't actually measure the absolute enthalpy, but we can measure the change in enthalpy during a reaction.
Right.
A negative H means heat is released.
Okay.
Exothermic. While a positive H means heat is absorbed.
Endothermic. Okay.
So when you burn a log in a fireplace, that enthalpy change, the H, is negative because it's releasing heat. It's making the room warmer.
Okay, that makes sense. So how do we take these enthalpy changes and incorporate them into chemical equations? Is that where thermochemical equations come in?
You got it. Thermochemical equations include the enthalpy change, the H, right alongside the balanced equation. For instance, the textbook gives the example of the combustion of methane. CH4G plus 2O2G yields CO2 plus 2H2O. HECOM equals negative 891 kiloj.
Whoa, that's a lot of energy released just from burning 1 mole of methane.
It is. And notice the physical states are included in the equation. Gas, liquid.
Why is that important?
Because the physical state of a substance can influence its energy content. The way particles are arranged, how they move around, it all differs between solids, liquids, and gases. And that affects the energy involved in a reaction.
So burning methane gas would release a different amount of energy than, say, reacting methane in liquid form.
Exactly. Physical states matter, and thermochemical equations capture those details.
All right, that makes things clearer. But what if we have a more complex reaction where it's not so easy to measure the enthalpy change directly?
That's where Hess's law comes in handy.
Hess's law.
Yeah, it's a powerful tool that lets us calculate the enthalpy change for a reaction. But we use a series of simpler reactions.
So instead of measuring the enthalpy change for a complex reaction all at once, we can break it down into smaller steps.
That's the idea.
Okay.
Hess's law states that the total enthalpy change for a reaction is the same regardless of the pathway taken.
Okay.
Imagine you're hiking up a mountain.
Oh, I like this analogy.
You could take a steep, direct route. Or you could follow a winding path with several switchbacks.
Right.
No matter which path you choose, the change in altitude, which is kind of like the enthalpy change, is the same.
Oh, okay. That makes sense. So we can add up the enthalpy changes for a series of simpler reactions that lead to the same overall reaction.
Yeah.
And that gives us the enthalpy change for that more complex reaction. It's like solving a puzzle by putting together smaller pieces.
Exactly. And sometimes we don't even need to measure those enthalpy changes for those simpler reactions directly. We can use what's called standard enthalpies of formation.
Standard enthalpies of formation.
Yeah, it's like having building blocks for enthalpy calculations.
Okay, so what are those and where do we find them?
They represent the enthalpy change when 1 mole of a compound is formed from its elements in their standard states.
Okay.
Think of it like the energy cost to build a molecule from scratch.
Right.
And these values, they're readily available in tables.
Oh, nice.
And we can use them to calculate the enthalpy change for any reaction using a pretty simple formula.
That's convenient. But what about those little degree symbols I always see next to the enthalpy?
Ah, good eye. Those indicate standard conditions. 1 atmosphere of pressure and 25 degrees Celsius.
Oh, okay.
Because enthalpy changes can vary depending on the temperature and pressure. So it's important to be specific about the conditions.
Right.
You got it.
So by using Hess's law, or these standard enthalpies of formation, we can figure out the enthalpy changes for tons of reactions, even the tough ones that are hard to measure directly.
Exactly.
But does a negative H automatically mean a reaction will just happen spontaneously?
Ah, that's a great question. It leads us to a really crucial concept. Reaction spontaneity. It's not just about enthalpy, entropy also plays a key role.
Right, let's talk entropy then.
Yeah.
What is it and how does it factor into whether a reaction will happen on its own?
Entropy, which we denote by S, is basically a measure of disorder or randomness.
Disorder?
Yeah, think of your bedroom. The messier it is, the higher its entropy.
Mine definitely has high entropy then.
Oh. But what does a messy room have to do with chemical reactions?
Right. Good question.
It's all a metaphor for the level of disorder in a system.
Okay.
The more ways you can arrange those particles, the greater the disorder. And it turns out the universe loves disorder.
The universe likes a mess.
It does. There's this thing called the second law of thermodynamics. It states that the total entropy of the universe always increases in a spontaneous process.
So things naturally tend to get more chaotic.
You got it.
Okay.
And a spontaneous process, well, that's one that happens without any ongoing outside intervention.
Okay.
Like ice melting at room temperature or a gas expanding to fill its container.
So if a reaction leads to an increase in entropy, meaning things get more disordered, it's more likely to be spontaneous.
Exactly. Several factors can increase entropy. Phase changes, an increased number of particles, higher temperatures, even dissolving a solid in a liquid.
Okay.
Imagine dropping a dye tablet into some water. Okay, yeah.
Those dye molecules become more dispersed, increasing disorder and entropy.
So, if a reaction creates a lot of gas, that would have a positive change in entropy, making it more likely to happen spontaneously.
You nailed it. But both enthalpy and entropy contribute to a reaction's spontaneity.
Right.
Their interplay is captured by something called Gibbs free energy.
Gibbs free energy. Yep,
we denote that by G.
Right.
It's the energy that's actually available to do useful work.
Okay.
And the change in Gibbs free energy, G, well, that tells us whether a reaction will be spontaneous or not. And we can calculate it using the equation. G equals H minus D.
So we're taking into account the heat change, which is enthalpy, and the change in disorder, which is entropy, along with temperature. So what does the value of G actually tell us about spontaneity?
Well, a negative G, that means the reaction is spontaneous. A positive G, that means it's non-spontaneous. And a D of 0, well, that indicates equilibrium.
So a negative G is like a green light.
For a reaction to happen spontaneously. But a positive pedal means it needs some help.
Yeah, like adding heat or energy.
Right.
And you're right, temperature plays a big role here, too.
Okay.
Temperature can actually tip the scales between enthalpy and entropy. For example, even an endothermic reaction, where it absorbs heat, it can be spontaneous at high temperatures if it leads to a large enough increase in entropy.
That makes sense. It's like adding enough heat to overcome the energy barrier and let the reaction proceed towards more disorder.
Exactly.
Can we see this in action with like a specific example?
Sure. Let's consider the formation of ammonia from nitrogen and hydrogen gas. So N2G plus 3H2G yields 2NH3G. The AH for this reaction is negative 91.8 kJ, and the A is negative 197 JK. Let's calculate AG at 298 K, which is room temperature.
Okay, so first we have to convert AH to KJK, right? Okay. Giving us negative 0.197 kJ. Then we just plug all the values into the equation. AG equals H minus TS. So that's negative 91.8 kJ minus 298 K times negative 0.197 kJ.
And that gives us an AG
of negative 33.1 kJ.
Exactly. And since low G is negative, we know that reaction is spontaneous at 298 K.
So even though this reaction becomes more ordered with a negative entropy change, that large negative enthalpy change where it releases a lot of heat, that makes it spontaneous at room temperature.
Precisely. So you can see how spontaneity really depends on this complex interplay between enthalpy, entropy, and temperature.
It's fascinating.
It is. And understanding this interplay is key for predicting and explaining how these chemical reactions behave.
Well, we've covered a lot of ground already, from basic energy concepts to the complexities of enthalpy, entropy, and Gibbs free energy. It's amazing how these concepts connect to explain why some reactions happen spontaneously and others don't.
And we've only scratched the surface. There's a lot more to explore, like specific types of enthalpy changes and how these concepts are used in different fields.
Well, we've definitely given our listener a lot to think about. But don't worry, we'll be back soon to continue this deep dive into energy and chemical change. Welcome back. Last time in our deep dive, we really explored some of those foundational concepts of energy.
Heat. Enthalpy.
Entropy.
Gibbs free energy.
All those good things. It was kind of like, I don't know, opening up the hood of a car and seeing all those parts that make it go.
Yeah, and we saw how understanding all those parts and how they work together can help us predict whether a reaction will happen spontaneously. Like knowing whether your car will start when you turn the key.
Exactly. So now I'm ready to take this understanding to the next level. Can we dive a little deeper into some specific types of enthalpy changes? I feel like that's where things could really click into place.
Absolutely. Let's start with enthalpy of combustion, or HCOM. This refers to the enthalpy change when 1 mole of a substance completely burns in oxygen.
So it's like measuring how much heat is released when you burn a certain amount of fuel, like propane in a grill.
That's a great example. Enthalpies of combustion are often used to compare the energy content of different fuels. Like if we compare the HCOM of methane and propane, we could see which one releases more energy per mole when burned.
That's super practical. It's like choosing between, regular and premium gasoline based on which one will give you more bang for your buck.
Exactly. And speaking of practical applications,
Okay.
let's talk about phase changes. You already mentioned specific heat, but there are also specific enthalpy changes associated with those transitions between solid, liquid, and gas phases.
Okay, so we're talking about things like melting ice or boiling water.
Precisely. We have what's called the molar enthalpy of vaporization,
Okay.
or HVAP, and that's the heat required to vaporize 1 mole of a liquid at a constant temperature and pressure. Think about the energy needed to turn a pot of water into steam.
So it's the energy needed to overcome those forces that are holding those liquid molecules together and allow them to escape as a gas.
Right. And similarly, we have the molar enthalpy of fusion, or EFIS. This refers to the heat required to melt 1 mole of a solid at its melting point.
It's like the energy needed to break apart that tightly packed structure of ice and let the water molecules flow freely.
Exactly. Each substance has its own unique enthalpies of fusion and vaporization, depending on how strong those intermolecular forces are holding its particles together. And we can actually measure these enthalpy changes using calorimetry, just like we discussed for reactions.
So if we carefully measure how much heat is absorbed when a known mass of ice melts, we can calculate the emphasis for water.
Precisely. These values allow us to understand and predict how much energy is needed for these phase transitions. Whether it's the ice melting in your drink or the water boiling on your stove, these concepts are at work all around us.
It's amazing how these, seemingly abstract concepts have such concrete and everyday applications. Speaking of applications, I'm kind of curious about how these principles relate to energy production and consumption on, a larger scale.
That's a great point. Consider the burning of fossil fuels, which is still a major source of energy worldwide. When we burn coal, oil, or natural gas, we're essentially harnessing the enthalpy change of that combustion reaction to generate electricity or power other processes.
So we're releasing the stored chemical energy in those fuels as heat, which we then convert into other usable forms of energy.
Exactly. But as you know, there are downsides to relying on fossil fuels, primarily the release of greenhouse gases that contribute to climate change.
Right, which is why there's this big push for renewable energy sources like solar, wind, and hydropower.
And you know what? The principles of energy and thermodynamics are crucial for understanding how these technologies actually work and for optimizing their efficiency. For example, solar panels convert light energy into electrical energy, and they rely on the principles of energy transfer and conversion that we've been discussing.
So even though we might not be directly calculating enthalpy changes or Gibbs-free energy in our daily lives, these concepts really are the backbone of so many technologies we rely on.
Absolutely, and they're also at the heart of material science and engineering.
Now that you mention it, I do remember the textbook mentioned something about enthalpy and entropy playing a role in the properties of materials.
You're right. Think about it. The melting point, boiling point, hardness, conductivity of a material, these are all determined by how its atoms and molecules interact with each other.
And those interactions are governed by energy, right?
Exactly. For instance, if we want to design a material with a high melting point, we need to choose atoms or molecules that form strong bonds with each other.
Okay.
Those strong bonds will require a lot of energy to break, which will result in a high melting point.
So understanding the enthalpy and entropy of a system can help scientists make materials with specific properties for all sorts of applications. That's so cool.
It really is. From the clothes we wear to the electronics we use, these principles of thermodynamics are woven into the fabric of our material world, and we've only just begun to explore the possibilities.
Well, this deep dive has definitely taken our understanding of energy and chemical change to a whole new level. We've explored those specific types of enthalpy changes, seen how these principles are applied in energy production and material science, and gained a much deeper appreciation for how interconnected these concepts really are.
And as we move into the final part of our deep dive, we'll tackle this concept of equilibrium and how it relates to energy and spontaneity. We'll also explore some of the limitations of, classical thermodynamics.
And we'll get a glimpse into this fascinating world of statistical mechanics.
Sounds like we have even more amazing territory to cover. Until next time, keep those mental gears turning. Welcome back for the final part of our deep dive. We've been exploring this amazing world of energy and chemical change.
We've gone from those basic laws to how they actually play out in the real world.
Exactly. And now we're going to tackle this idea of equilibrium. It's like the glue that holds it all together.
Equilibrium is this fundamental concept in chemistry. It describes a state of balance in a system.
Balance, okay. Think of it like a tug of war, where both sides are pulling with equal force so nobody's winning.
A standstill.
Right. Now, in a chemical reaction, equilibrium is reached when the forward reaction, that's where reactants turn into products, and the reverse reaction, where products turn back into reactants, happen at the same rate.
Okay, so it's not that the reaction has stopped. It's more like things are happening at equal speeds in both directions.
Exactly. At that point, the concentrations of reactants and products, they stay constant. It's like this dynamic balance.
Okay, so picture this. A busy intersection with traffic flowing in both directions. But the number of cars on each side stays pretty much the same.
Perfect analogy. Now, how does energy fit into this picture? Remember Gibbs' free energy?
Of course. It tells us if a reaction will happen spontaneously or not.
Right. Well, at equilibrium, that Laggy is 0.
So neither the forward reaction nor the reverse reaction is, favored.
Yep. It's like a perfectly balanced seesaw.
I like it.
And since G equals HH minus TIS, we can rearrange this equation at equilibrium to get AH equals TTES. This tells us that the enthalpy change of the reaction is totally balanced by the product of temperature and entropy change.
So it's this super intricate dance between enthalpy, entropy, and temperature that sets the equilibrium point of a reaction.
You got it.
But we can mess with this balance a bit, right? What about that Le Chatelier's principle?
Good one. Le Chatelier's principle states that if we change something in a system at equilibrium, it'll shift to try to counteract that change.
Like the system is trying to stay balanced.
Exactly. So if we add more reactants, the system will shift to use up those extra reactants and make more product.
Kind of like adding more weight to one side of that seesaw.
Precisely. It's always trying to get back to equilibrium. And we can actually use this to our advantage in a lot of industrial processes. By changing the temperature or pressure, we can push the equilibrium in the direction we want.
Wow, that's amazing. Okay, so we've covered some serious ground with these fundamental concepts, but are there any, limitations to these ideas? Do they always hold up?
That's a really thoughtful question. And honestly, classical thermodynamics is super powerful, but it does have its limitations.
Okay.
It's what we call a macroscopic approach.
Macroscopic.
Meaning it looks at those big picture properties of a system, like temperature, pressure, volume, but it doesn't really delve into the tiny world of those individual atoms and molecules.
So it's like describing a city by its skyline and population, but not really seeing the lives of the people who live there.
Exactly. We get this overall view, but it doesn't explain everything. Like, why do some substances have the specific heat capacities they do? Or why some reactions have those particular entropy changes?
So to get to those answers, we need to zoom in, way in. Look at how each particle behaves.
Exactly. And that's where statistical mechanics comes in.
Statistical mechanics.
It uses these statistical methods to connect the macroscopic properties of a system to how the particles behave. Think of it as bridging that gap between the big world we observe and that tiny world of atoms and molecules.
So instead of just measuring the temperature of a gas, we look at how fast each gas molecule is moving.
Exactly. And by understanding how those particles' energies and positions are distributed, well, we can actually calculate those macroscopic properties like temperature, pressure, and entropy.
That's incredible. It's like taking a closer look at that city we were talking about and seeing the network of streets and buildings.
Exactly.
And all those people.
Statistical mechanics has been a game changer for how we understand thermodynamics. And it's used in tons of different areas. It helps explain things at that molecular level and predict how complex systems will act.
This deep dive has been an amazing journey. We've explored those core laws of thermodynamics.
The different kinds of enthalpy changes.
The whole concept of equilibrium. We even touched on those limitations of classical thermodynamics and the insights that statistical mechanics has brought us. It's incredible how energy drives change in everything around us.
Absolutely. And as you've seen, these aren't just some abstract ideas. They impact how we understand everything, from everyday things to these big scientific discoveries.
Well, we've certainly given our listeners a lot to think about. This deep dive has hopefully made you curious to learn even more. Remember, this is just the start. Keep asking questions, keep learning, and keep exploring the awesome world of chemistry and thermodynamics.